What's up, people? This is Robert Bassano. I'm bringing this video to you guys today. I decided to look into some questions and answers on physics. So I'm going to end up dialing the Brookhaven National Laboratory in the United States for the U.S. Department of Energy. Let's ask them some questions regarding some answers we need on dark matter, antimatter, particle acceleration. Let's see what they have to say. Okay, let's see what's going on here. So as you guys can see, here are all the numbers for the general labs. Let's see who answers the phone.
Erica Lamar.
I'm sorry, who am I speaking with?
Oh, this is Erica Lamar.
Erica Lamar. Are you a scientist in the physics department?
Yes.
How you doing? My name is Robert Bassano. I'm a graduate student studying applied physics.
Oh, hi. How are you?
I'm good, Erica. Now, what's your position with Brookhaven?
I'm actually administrative assistant.
Oh, so
Actually, I'm covering for Tracy, which is her number right now, the one that you just called.
you're covering for who?
I'm covering for Tracy Trent.
Tracy Trent. And what? She's the head of the physics department?
She's just the assistant of the department chair.
She's the assistant of the department chair. Who's the department chair?
It's Lawrence Lindenberg.
Lawrence Lindenberg. For nuclear and particle physics?
Well, I believe so. Yes.
Okay. Erica, okay. I was wondering if you can answer a few questions for me that I have with regard to, and it's just, I've read some of the open source information, with Brookhaven on your studies in dark matter, antimatter, particle acceleration. Unfortunately, there's no listed information for CERN in Switzerland. So, being a U.S. citizen, I figured I'd decide to call Brookhaven since you guys are leading up the program in the United States. On dark matter, I wanted to confirm because I was reading some data on, they also name it dark fluid.
Oh, okay.
Would that be correct?
I have no idea, but the right person to talk about it is he's actually out for today. But I could give you his the department chair's number if that's okay.
Would the department chair be able to answer the question?
Yes, I could give you his number. His number is let's see, it's 631. 344.
344.
2700.
2700. And the department's chair. I'm sorry.
Actually, hold on for a second. I think I gave you the wrong number. This is like two numbers here. Let me see.
Okay.
The last four numbers is actually 3811.
And the department's chair name is what?
Lawrence Lindenberg.
Lawrence Lindenberg?
Yes.
So it's 344. What was it again?
It's 631 344 3811.
3811. Okay.
Mm-hmm.
Thank you very much, Erica.
You're welcome.
All right. You too. Bye-bye.
Thank you. Bye.
So, Erica's answering the phone for the physics department, and she can't answer the question on dark matter. Physics. Brookhaven National Laboratory. So we're going to call the department chair. Let's see what they have to say.
Hello?
Yes. Lawrence?
Yeah.
You're the department chair for the physics department, nuclear and particle physics for Brookhaven?
At the moment, yeah.
Okay, sir. My name is Robert Bassano. I'm a graduate student studying applied physics. I'm actually also working on a graduate certificate in artificial intelligence. So,
Yeah.
I spoke with Erica Lamar, who answered the phone for the physics department, and it was specific to a paper that I'm working on with regard to dark matter, also known as dark fluid. And I've read some
I
of.
never heard that term.
I'm sorry.
I never heard the term dark fluid.
Yeah, I hadn't heard the term before either, but when I was conducting some of the research, there was one particular paper that addressed it as dark matter, aka dark fluid. It was, I don't recall the university off the top of my head, but
Yeah, all right, go ahead. I just
I was trying to call CERN, but they have no listed information to speak to anyone regarding the subject. But being a U.S. citizen and student, I figured I'd call the top laboratory in the United States. So,
well, you know, I would say we're not the top laboratory in the United States for that kind of study.
okay,
All right. In fact, we're probably near the bottom.
really?
Yeah. I mean, it's not. It's a small enterprise here. You know, we do many other things.
Okay,
The labs that do this the most, well, Berkeley, LBL, Fermilab does a lot of it.
okay,
Argon, Black, they do much more than us.
okay,
Okay, so and in fact, we have no one working on dark matter except in the sense that a couple of our theorists. Well, there's a few things I have to say. People do look for dark matter at colliders, and we have a group working on the LHC, and of course, you know, they look for that among 1,000 other things.
okay,
And some of the theorists have, they're touched on this, but we don't have any experiments that are really cosmological experiments the way other labs do.
okay.
They have dedicated experiments to look for direct interactions of dark matter, and
So do you think the Fermilab would be the best reference?
would be fine. And I'm trying to think.
Is there someone at the Fermilab you could recommend?
Well, yeah, Fermilab. Who works on that at Fermilab? I would have to look it up. None of my friends work on that. But in Berkeley, for example, Natalie Rowe, who's the division director, she's an expert on cosmological stuff. Although maybe
Also, University of Berkeley?
The Lawrence Berkeley National Laboratory.
The Lawrence Berkeley National Laboratory. Let me see.
It could be called LBL. I'm trying to think of who does dark matter. I mean, I don't know. I guess I didn't let you finish on what you're trying to find out.
Well, I've been entertaining. Much of the research is taking me into considering helium-4, superfluid helium-4. Combining that with what a company in UK has developed called Vanta Black that absorbs 99.96% of all visible light.
Yeah, I've heard of that.
Yeah, so what I'm looking into is the possibility that, because this is a carbon nanotube type of structure, solid structure, I've been looking into the possibility that maybe this could also be developed in liquid form. And if you combine superfluid helium-4 with liquefied carbon nanotube Vanta Black, could this be? Because no one's clearly defined what dark matter really is.
I can assure you that's not dark matter.
Well, no, I'm not trying to insinuate that this is dark matter, but you bring a point. There's no science.
Dark. It doesn't make it dark matter.
No,
What they mean is it doesn't emit light.
Yeah, exactly.
It doesn't have any interactions that we can identify except gravity. Okay, so that's why they call it dark matter.
Okay, but how are they actually? The papers that I've been reading, the peer-reviewed and scholarly-reviewed work that I've been reading, there's no clear definition of what dark matter is or is not.
Well, we understand a lot of things about it, but we don't know what it is. So you can tell there's something there
Uh-huh.
because the stars and galaxies don't spin at the right rates, around the center, things like that. So it's clear there's more mass than you can see.
Yeah.
Okay, so that's how we know that it's there, and we know how much there is of it. Okay, which is 5 times more than all the visible mass.
Okay.
But in fact, for many years, it was in fact possible that this dark matter was baryonic. In other words, it wasn't anything exotic. Just maybe, you could imagine big clumps of matter floating somewhere in the universe, not emitting anything, and having been missed by various probes over the years, and that got eliminated. So the thought now is that it's got to be something new. Okay, so although even now, I think there's some people advocating maybe neutrinos, some sort of neutrinos might be it. They would be not the normal kind of neutrinos, but what's called sterile neutrinos. There's also theories of what they call axions, which would be very, sort of almost massless particles, but so many of them that they could add up to this. And so, there's a lot of theories, but, we like axions don't have to exist. They're just a theoretical thing.
Wait. You said axions, they're theoretical, but they don't necessarily.
In other words, they were proposed by people to explain certain things. Okay, so they would be an explanation of certain other problems we have, and maybe they could be adopted to serve as the dark matter. But no one's ever seen any. There's a big experiment in process to find them. Okay, to see if they're there, and many experiments in the past have failed to see them. So that's one idea among many. Other ideas are some kind of particles that come out of a theory called supersymmetry.
Yeah, and then I've read. Yeah, it is very. I've read Dr. Gates's work.
Popular theory, but there's less. It seems more and more far-fetched. People haven't been able to see any of the other particles predicted by supersymmetry, and so it's not that you can. It's a very rich theory. You can't falsify it, at least not very easily, because you just keep pushing the mass scale up. But it was proposed to solve a certain problem,
Okay.
and it's being pushed to a point where it can't really solve that problem, and so.
And that's why it remains theoretical.
Yeah.
So here's it, and this is interesting what you're telling me, because if all of the papers that I've read, a dozen or so, peer-reviewed and scholarly from several different laboratories around the world, no one really knows what dark matter is. They know that there's something there, and the common denominator is it's invisible, but no one. I guess what I'm getting at is, if they know there's some sort of dark matter there, I'm tending to believe and understand that there's something there. It can't be seen. The term dark matter has been used to codify and classify whatever it is that is there, that can't be defined. However, when someone,
right now we can't.
yeah, but when I'm alluding to the option that superfluid helium at absolute 0 degrees Kelvin with zero viscosity could possibly be it.
No.
There are other colleagues that I have and other scientists that I spoke to at NASA where they actually are now. I mean, literally, one of the scientists I spoke to, who's part of was part of a very large program where they're looking into this. the first issue he brought up was, okay, what kind of densities are we talking about here? And density was really a moot issue because at 0 degrees Kelvin, superfluid helium is zero viscosity. So you wouldn't be able, you might be able to, what we're defining as being to look out into space and see that there's some sort of warping, but we can't, and we can see through it, but we don't know what is actually there that's creating that sort of.
The thing is, the hydrogen would be excited if it was at 0, which it can't be, but if it was near 0, it would be excited by photons streaming through.
Yeah, and I agree with you. I agree with you on that.
And it would re-emit. People have, there's a lot of hydrogen in the universe. There's hydrogen clouds. People see them all the time.
Yes, exactly.
And they also know, because of very complicated theories that bear on how elements were created, and in the present theory of the universe, sort of universe's evolution,
Mm-hmm.
we know about how much hydrogen there has to be. Okay.
Within dark matter,
why?
do you theorize that dark matter actually exists? Hydrogen can exist in the same space as dark matter, or could it be void of hydrogen?
So, in other words, everything can exist. Everything we know of can exist in space of dark matter, going through us all the time. That's what we're pretty sure of. So it can exist, it can go through the hydrogen just like it can go through any other matter.
Because
you could get confused because people are using superfluid helium or anyhow near that for detectors of dark matter. Okay.
Yeah.
And that may give you the wrong impression, but nobody thinks that it's a candidate for dark matter.
Well, there's a recent study put out in a university paper by a bunch of students at University of Maryland, and I think it was Berkeley, where they actually they put superfluid helium in a vacuum environment, controlled setting. So when you look at that dependent variable of putting superfluid helium in a vacuum and then dropping it down to close to absolute zero as possible, that means that the hydrogen and whatever gases are being removed.
Wait a minute.
Is that correct?
Okay, so
Am I correct to say that? Because that's what the experiment explained.
Do that, but I don't understand what the implication of that is. Sure,
the implication is that superfluid helium,
vacuum,
yeah,
all the time.
Superfluid helium changed its structure and composition when you removed hydrogen from the equation.
It has several phases, okay, and it can go from one to the other under various conditions. But I don't understand what bearing this has on dark matter.
Well, what bearing this has is that
dark matter.
Yeah, and that's what my paper is based on, is the fact that I factored in the science that's already agreed upon, that the universe, there's hydrogen everywhere that is being excited, but when you bring superfluid helium down to close to absolute 0 degrees Kelvin, we can't do it on Earth, of course, but you get it down as close enough as possible, and you put it in a vacuum environment.
Let me tell you this: the theory, I mean, the whole structure of the cosmological theory, from which we, extract the fact that there's 20% of the energy of the universe is in dark matter. That whole structure is based on a certain theory called cold dark matter. Okay, and it has a number of implications, and one of them is how much helium there should be in the universe.
Okay.
Okay, and there is about the right amount. There's not going to be 100 times more. Okay, otherwise the whole structure doesn't make any sense.
Okay. And this has been already proven and theorized.
Yeah, in other words, the elemental abundances are one of the things people build a theory on.
Okay.
Okay, so there's so much helium, they know, there's so much hydrogen, and so on. And some of those things are a tiny bit wrong. You know, the observation's a tiny bit hard to explain. They're not exactly on, but we're not talking about something 100 times bigger, you know, in the amount of helium that's around.
Mm-hmm.
You know, yeah, sure, possibly it could all be wrong, and there could be another theory that in which you know, explains everything that the standard theory explains.
Yes.
But has a lot more helium. But that's not what we, you know, that's just very far-fetched, and so.
Okay.
You know, anyone who came up with a theory like that would then have to explain all the other facts that the current theory explains, okay? I mean, that's the kind of thing that drives us toward the idea that whatever dark matter is, it's not in our current bestiary of particles. Okay, it's got to be something we've never seen.
Yeah, because there's been studies out, for example, over in the UK, where researchers in Switzerland and UK mapped dark matter in clusters, and they discovered that the dark matter might be, you know, just not behaving as the way they expected. They think it may not be particles at all. It may be some sort of fluid. And it's actually from one of the universities that I'm considering pursuing a PhD at the École Polytechnique Fédérale de Lausanne, EPFL, in Switzerland. They're the ones who came up with that idea that it could be fluid.
You might consider the axion field as a sort of fluid. I don't know what else they're thinking, but whatever it is, it could be a fluid, I suppose. But it's yeah, I mean, I suppose it could be.
Yeah, I think it may be a combination of things, but and that's why I'm focused on superfluid helium.
There's some number of dark matter, you know, particles. If these particles are what we think from supersymmetry, there might be 1 per cubic centimeter around here.
Mm-hmm.
You know? So it would be a very, very thin fluid, indeed. But you know, and certainly if it's really made up of very, very low mass things, it could be more and more like a fluid. If it's made up of 100 GeV particles, the way people, you know, probably still the more popular idea, then it's not much like a fluid. But you know, there's many, many theories.
Yeah, because I mean, there was something interesting that I conducted a comparison on just the other day. I did a video comparison of the experiment that was conducted at the University of Maryland in a laboratory, and
what was the purpose of that experiment?
The purpose of that experiment was to reveal the quantum vortices, the high speed whirlpools, I should say, or tornadoes, they said,
that's possible, sure.
where at nearly 0 degrees Kelvin, all of the electrons and atoms and neutrinos, everything moves in one direction, and that's what's creating the zero viscosity. And then what they did was injected some sort of other nanoparticles and shot a laser inside the container.
As I said before, the interest in, say, low temperature helium for this is really as a detection medium. So, for example, people have ideas of using it as what they call a bolometer, where they look, you know, you get things as close to possible to absolute zero, and then you look for something got hit, and therefore there's a little bit of energy in the system.
Exactly.
If you have a super duper, you know, thermometer, sort of, you can tell, and you can use that, you know, to look for dark matter interactions. Okay, so that's the sort of relevance of that stuff to dark matter. And if you look on the internet for dark matter experiments, you might find something like that. I really don't know if that has been pursued. People use many, many technologies, and in proposed dark matter searches. But in recent years, the government has only agreed to fund. The U.S. government has only agreed to fund 3 experiments. One is the Axion search, called ADMX, and the other one uses crystals like silicon and something else, and the other one uses liquid xenon. Okay, and so that's a similar idea. The only thing is that xenon, I'm not sure, helium probably does it too, but xenon, if there's an interaction, it emits light, and so you can see the light, and it also ionizes things, and so you can detect the ions by their charge. So
yeah, because
maybe the whole thing could be done in helium, but for various reasons, people seem to want heavier liquids like xenon, probably just because you need a big target, and these experiments use like tons of material.
Well, the interesting video that I put together did a side-by-side comparison of thermal imaging of a space video that was shot of all of the stars in the background on an STS mission, and you could see how it looked like sort of particles just moving around the sky. And then I put that video side by side with what they did at the University of Maryland, where they injected laser light into the superfluid helium with some other particles to show the quantum vortices. And when you look at them side by side, Lawrence, oh my God, you couldn't tell which video was actually in a control setting and which video was actually space.
Or, the same equation will characterize much different, systems. That's not unknown. There might well be a relation, but I don't think it has much to do with dark matter.
Yeah, but in this particular instance, they were using superfluid helium, and it was just, I had showed a friend of mine. I said, could you tell which one of these videos was in a controlled laboratory setting, using a fluid, and which one is actually space? And he looked at both and he says, well, which one is which? I'm like, well, can you tell which one is actually a space video shot on the night side from the STS, and which one was done in a laboratory with superfluid helium-4? He says, the one on the left is, I said, the one on the left is what? He says, the one on the left is space. I said, so you're saying the one on the right is a laboratory superfluid helium? And he says, yeah, I'm pretty sure of it. I said, you're wrong. The one on the right is space. The one on the left is a laboratory. He goes, oh my God.
Well, as I say, that can be an accident, or it could be that there are actually similar equations governing the systems.
And that is what I'm want to try to get at. When you say similar equation, could you be more specific? I mean, what?
I have no idea. I mean, about what the equations governing superfluid helium vortices in superfluid helium are, but they may be similar to whatever it is you were looking at in space. It's just, I don't know. It just has to do with fluid dynamics.
Yeah, and it was that video they did at University of Maryland was a fluid dynamic experiment.
Yeah. Well, as I say, I think your best bet is to look into liquid helium as a detector. Find out why they don't use it. If it's just big, I have to say, it's all those experiments were motivated by the idea of this supersymmetric particle, which you can calculate the interaction cross-section.
Yeah.
And there were reasons why that seemed reasonable at the time, but it seems less and less.
How close
promising.
Are you aware of any studies or research they may be doing on the ISS where they're trying to maybe conduct some sort of tests whereby they can make a determination.
Well, there are experiments there, that particularly the one by Sam Ting and a cast of thousands. What's it called? I don't remember, but it is looking for signals from dark matter annihilation. Okay, so they look for they look for a couple of things. One is they look for positrons coming from space, which could be conversions from photons coming from the annihilation of dark matter. The one idea, there have been various claimed signals, unexplained lines in spectra, which people say, well, that could be dark matter self-annihilating. You know, if two of them
now
together, they could annihilate.
The quoted.
So they look for that. So that's definitely on the space station.
So the quoted, the statistic you gave on the composition of, the universe being 20% dark matter. Where could I find that statistic data?
Just look up any.
So it's 20%.
Look up cosmology. Look up cosmology.
Yeah, because I have looked it up, and there's a disparity in the numbers. Some are saying 70%, some are saying 20%, and some are saying that it's 80%.
70% is, nobody says 70%. The 70% you're quoting is dark energy, not dark matter.
Yeah, because the paper I'm looking at right now says that dark matter appears to make up at least, and they're just guessing, of course, at least 80% of the matter in the known universe.
Yes, but that's not the whole picture. The energy
of
the universe is 70% or thereabouts dark energy. The rest is matter of one kind or other, most of which is dark matter. Okay, this is elementary stuff which you should be able to find all over the internet.
Yeah.
Just look up cosmology.
Well, yeah, some of it's just, I'm not saying it's confusing, but they're not being very concise and definitive when they're using the term.
Much of this stuff. But again, I'm not an expert, so I can't tell you the best references for that.
Yes, sir.
But if you look up cosmology and, look at somebody who comes from a major university, you're writing like a review article, that's where you'll get the
Now, who was the person at Berkeley you said I could speak to?
Or as I say, call up the physics departments of...
Yeah, who was it at Berkeley you said that I could speak to?
There's a woman, I don't know if she'll speak to you, but her name is Natalie Rove. She's really more of an expert on dark energy.
Natalie Rove.
Yeah, I'm trying to think of the name of the people that are very interested in dark matter. Well,
yeah, because I'm on their website right now, and it doesn't appear that she's actually part of the lab leadership.
She's an ALD. Are you kidding? ROE.
Yeah, because I'm on their lab leadership web page right now on Berkeley Lab, and they're only showing the director, deputy director, leadership team.
Who do they have as director?
They have Michael Witherell.
Yeah, okay, so at least that's up to date. Well, maybe she was overturned in a palace coup, but
yeah, I knew you were getting ready to use a coup. I knew it. I knew you were getting ready to say that.
And a couple of months ago, she was the ALD. Let's see, LBL.
I knew you were going to use the word coup. That word was in my head, and I'm like, was there some sort of coup? Was she ousted or something?
Well, on the first page, there's a story about dark matter. Don't you see it?
For the Berkeley Lab.
Yeah. Just do www.lbl.gov.
I'm on it right now. Let me go to their first page.
Mike?
Yeah, Hunting for Dark Matter's Hidden Valley. That's Catherine Zurich.
Yeah, so she's a theorist. Let's see. The leadership team, as you say. So Mike, yes, Mike. Or Simon.
Have they been able to measure dark energy?
Yeah.
Now I'm gonna ask you sort of like a backwards question. Now, based on the conversation you and I are having, we agreed that dark matter can't be clearly defined. They don't know what it is. They're trying to detect signals to see where it is and where it may exist. But they've been able, so when I ask, have they been able to measure dark energy? How could you measure dark energy when you don't know what is actually creating the energy, if it's supposed to be dark matter?
It's by implication. They don't directly measure it. They see it by they see it by the fact that the universe seems to be expanding faster than the original prediction. The expansion of the universe seems to have started to accelerate about 1 billion years ago, and it's accelerating. And so,
yeah, I read a paper by Hubble, and he says that the universe is speeding away from us at 90 million miles a second.
Yeah, I know, but that's way out of date. In other words,
so what are the new numbers?
It's not that there's new numbers; it's new ideas.
Okay.
He had a sort of constant, whereas a constant speed, whereas it's actually accelerating. That speed is getting faster and faster. If you look on the org chart of on that webpage, you'll see
Leadership Organization.
Diamonds, yeah, N.A. Rowe, that's her.
Okay, org chart.
Yeah, but as I say, I'm not sure she's the right person to talk to. You might call her office and ask who works on dark matter.
Okay. Oh, wait a minute. What'd you say? Look under.
See, there's an org chart.
Yeah, I'm looking at the org chart. Look under physical sciences, right?
Yeah, look on physical sciences at the bottom.
N.A.O. Rowe. That's her? That's her?
Yeah, that's her.
Okay.
Yeah. So anyway, her office should be able to tell you who works on dark matter, and that's who to talk to.
Perfect.
Okay.
Conversation was definitely enlightening. Thank you very much, sir. I really appreciate it.
You're welcome.
Take care.
Bye-bye.
Bye-bye. You heard it, people. They don't even know what dark matter is. But somehow they're implying that they can measure dark energy. How the hell can you imply that you can measure dark energy when you don't even know what the fuck dark matter is? You don't even know. And when I proposed to him that it's a possibility, it's a combination of a substance called Vanta Black, which is a carbon nanotube structure that could be in a liquefied form, combining it with superfluid helium at 0 degrees Kelvin. He said immediately, no, it's not a fluid. And there you go. I show the article from a Swiss university, which basically says that dark matter makes up about 80% of the known matter in the universe. He says it's 20%. There's other studies I found where it says 70%. And here you have one of the top universities. This EPFL is literally the MIT and Caltech equivalent in Europe. And they're saying, through their research, is dark matter a fluid? Mystery particles are mapped in galaxy clusters, but results suggest they may not be particles at all. This is from the UK. That's what he said. And here goes this damn bullshit ass Hubble again. Doesn't make any sense, man. It just doesn't make any sense. They have no idea. The whole science of physics is bullshit. But I'm going to call this lady, and I'm going to see exactly what she can be able to tell me, since she's supposed to be the expert. Okay? She's supposed to be the expert at the Berkeley Lab, Lawrence Berkeley National Laboratory. I'm going to see what she has to say. Stand by. Yes, Natalie Rowe, or should I say Dr. Rowe?
She is actually on vacation until Monday. Can I help you with something?
She's on vacation. Is there somebody else within the department I could speak to on dark matter?
Yeah, let me give you Kevin Lesko's information.
Yeah, because I just spoke to Brookhaven, and I spoke to their acting director, and he said that she was the subject matter expert on this. So, and I'm a graduate student working on a research paper involving dark matter and dark energy. So I really do need to speak to someone if possible.
Okay, hold on 1 second, please. Okay, Kevin Lesko can be found at 510.
Wait, hold on. 510. Hang on. That's his full, what, 510, go ahead.
486
486
7731.
7731. And what's his name again?
His name is Kevin Lesko, Lesko.
Kevin Lesko. Perfect. Thank you very much.
Okay.
Thank you.
Welcome.
Bye-bye. So let's call Kevin Lesko. Kevin Lesko. Yes, Mr. Lesko, or Dr. Lesko.
Yes.
How are you? My name is Robert Bassano. I'm a graduate student. Hey, how you doing? I'm a graduate student working on a research paper on applied physics, and the subject matter is dark matter, possibly dark fluid, and I'm trying to integrate superfluid helium-4 and a substance that has been termed as Vanta Black. It's carbon nanotubes. So I'm trying to develop a competing hypothesis where if carbon nanotubes, Vanta Black, could be put into liquid form and combined with superfluid helium, could it be plausible and possible and proven that dark matter, this could be what dark matter may be? And I spoke to Brookhaven National Laboratory, their acting director, and they said that Natalie was the subject matter expert on this and recommended I speak to her, but she's on vacation. So they gave me your number and said that you were the next guy to potentially answer this question, that some questions I may have on this and some theories, so that it can give me a better understanding. I understand that you guys are one of the top laboratories in the United States on this. Tried to call CERN, nobody's available, of course. So here's what Brookhaven shared with me in the last 30 minutes of the phone call. The general theory and consensus is we don't know what dark matter may be. It's just all theoretical. Okay? There's conflicting and competing ideas that Brookhaven says it's 20%. There's other research that says it's 70%. You know, that's what NASA's putting out. I was looking at some of the information they have. And then I just recently saw information from EPFL saying it's somewhere at least 80%. I'm not really interested in the volume of composition of the entire universe or what it may be, because the amount of data that I'd have to put together to even, you know, use that as part of my research would be a never-ending paper. What I'm more focused on is what Brookhaven shared with me, saying that dark energy could be measured and detected. Now, would you agree with that?
So dark matter and dark energy are two very different things.
Well, yeah,
Okay.
I'm with you on that.
And the numbers you quoted is if you look at the total mass energy of the universe, there's like 73%, which is 70%, 73%, which is dark energy, and what that's tending to do is to expand the universe. So it's pushing the galaxies, the whole fabric of the universe is being pulled apart.
Okay.
Increase in volume. And then dark matter represents about 23% of the total mass energy, and that tends to hold together and is clumped around where galaxies are. So it's responsible for holding the galaxies together much more than the normal atoms are.
Okay.
Normal matter makes up about 4% of the mass energy of the universe. Dark matter is about 5 times that. And we do know that it cannot be normal matter. It can't be made up of, the dark matter cannot be made up of protons and neutrons, because if that were the case, then at the very early universe, during the Big Bang and during the subsequent expansion and cooling down, that would have been very different boundary conditions, very different results than what we observe now. The structure, large-scale structure, would have been different. The evolution of nucleons would have been different if there were more protons or neutrons early in the universe. So we know that the dark matter has to be some exotic form of material. And presumably it's collecting around, or presumably it's been observed to be in many galaxies, clusters of galaxies. We assume it's homogeneous in the other galaxies, so it's going through us as well right now. But it is not a normal material, because if it were normal material, we would have observed it. So we've got experiments that are looking for the presence of the dark matter that would be in our own galaxy now, and we haven't observed it yet. So it's not going to be made up of the material that we know well. It's not going to be made up of materials made of protons and neutrons, but it's something different.
Well,
those are two different.
Are you familiar with what helium-4 at absolute 0 degrees Kelvin or close to it is actually doing on the atomic level?
I studied superconductivity in grad school, but I haven't done anything with it since then. Some of my colleagues are looking into using superfluid helium for a detector.
Exactly.
Yeah.
Well.
But that's a detector, but that is still made up of protons and neutrons.
No, and yeah, you're right. But here's the interesting thing, which piqued my interest, was that it has a 0 viscosity capability,
Yep.
and
crawls up the sides of those
yeah,
cylinders.
and the research says that on an atomic level, instead of things being excited so that they can be observed, everything's moving in unison in one direction at super high speeds. Which means that if you're looking out into the universe and you've already decided dark matter has to be something more exotic we can't observe, then
I
how?
didn't say we couldn't observe it. I simply said it's made up of protons and neutrons.
No. That's what I'm saying. I mean, it could be potentially made up of protons and neutrons, but they're all moving together, and that's why we can't see them. Is that possible? I mean, if everything's moving in unison, I mean, let me give you the example. If you had 100 people standing in a crowd and you got them all in one line, one perfect straight line, and you look down that linear path, would you see 100 people, or would you see one person? You would see one person.
Unless I'm measuring the gravitational pull of all of the people, because the gravitational pull is a long-range force.
Okay, so what if the gravitational pull was in unison with the actual?
We know that gravity adds, though, right?
I'm sorry?
We know that the force of gravity for different objects.
Yeah, exactly. It does add up. But when you look at superfluid helium and the way it's performing, it looks like there's an absence of some sort of gravitational, excitation, so to speak, meaning that there's nothing pulling it apart. There's nothing causing you to visually see anything else happening or on a nano or quantum scale. It's all.
So it's called dark matter because it's been observed through its gravitational impact on large bodies, and it's called dark because we have not observed the collisions of it with other material. If you wanted to accelerate helium, superfluid or otherwise, and collide it, it would still interact. The fact that it climbs up the side of a vessel is just an issue of its.
Well, yeah, it climbs up the side of a vessel because it's in a container. When you talk about space, free space, you're not. We don't know how big the container of space may actually be, depending on where you're determining where space is actually beginning, and that's
the nuclei inside of the helium will behave according to the forces we're aware of. They will interact gravitationally. They'll interact electrostatically if they're charged. They will interact with the strong and the weak nuclear force. So if one were to take atoms of helium in a superfluid form and collide them with other atoms, they would still interact through those forces.
And you're saying dark matter is not behaving that way.
Right. The only interaction we've seen so far is gravitation. We're looking for the presence of it through its weak interaction, and that has not yet been observed. But if these were normal helium atoms that make up the dark matter and are running through space, we would see the interactions of that helium through the weak interaction, the strong interaction, and electromagnetic. But we have not seen that.
Now, has the gravitational activity been monitored, observed, and measured?
The impact of dark matter, yes, absolutely.
And
first discovered in the 30s by looking at clusters of galaxies, and subsequently they've observed the impact of dark matter on individual stars inside of galaxies rotating edge-on that we can observe. We observed it through gravitational lensing, and it's also been observed through large-scale structures.
So it's being observed through gravitational lensing.
That's correct.
Now this is what the assumption that the light being observed is actually traveling through free space. Is that correct?
Well,
when we talk about gravitational lensing, go ahead.
Whatever field is there, regardless if it's empty electromagnetically or it's filled, gravity, the force of gravity will distort the space-time.
Okay, but what if I,
regardless of what's there,
what if I threw this theory at you? That what we're actually viewing with regard to respect to gravitational lensing, because when that was first put out into the public domain, I'm still having issues with it. What if I threw this theory out to you that what it was being observed is not in free space, because light does not travel in free space in a vacuum, period. It has nothing to interact with, unless you're talking about the excitation of hydrogen atoms and all other sorts of gases that are present out in space.
Electrodynamics is that the way that light works is a varying electric field that generates a time and spatially varying magnetic field, which then goes back again. So light is simply a time varying electric field that propagates through the creation of an analogous or a composite magnetic field. So if you're saying it doesn't go through free space, then all we know about E&M is wrong.
And that's actually where I'm trying to take this paper, to literally click the reset button.
Well, you'll have to rule out an awful lot of experiments.
Well, and not an awful lot. All I need to do is basically debunk and disprove the existence of dark matter as it's been theorized and give it an actual atomic structure of some sort of composition. The second I'd have to do is disprove gravity as a dependent variable. The third is to determine exactly under what conditions would what we're theorizing is possible. And the reset button is pushed. And I believe I have enough information collected from Brookhaven, from Berkeley Laboratory, EPFL, and Fermi Lab, and several other laboratories and other white papers that have been developed, because the literature review is telling me everyone's saying the same thing, and no one's gotten any closer to developing some sort of convincing hypothesis, competing hypothesis to say, you know what, everything we know is completely wrong, and we need to start over and reconsider the possibility that what we believed that it could not be could actually be a combination of what we've always been working on. And
well, I wish you luck in that paper. I don't think I've given you any data, so I'm certainly not.
No, I'm not. No, that's not true. I mean, you've given me a whole lot. You've given me a whole lot to consider, and that was the purpose of this call, was that I needed to speak to someone who had subject matter knowledge into the research of this discipline, so that I can make a determination. No, I'm not going to quote you in the paper. I'm going to go through the information you guys have on the website and read a lot more of the papers that you guys have put out to make a determination saying, hey, I want to work towards a new model, a new theory that could actually be considered and put together to be tested to consider a reset. Not to,
Okay.
have every other paper being, disregarded, but to consider a new theory. That's it.
I wish you luck and to see in your paper.
Thank you very much, sir. You have a good day.
Thank you.
Thank you.
You
Take
too.
care. Bye-bye.
Bye-bye.
You heard it, people. You heard it. He's telling me if I tried to write a paper to debunk everything that they've been theorizing and putting out into the sciences, it'll basically fuck up all the work that they've been putting in to trying to prove something they know doesn't fucking exist. Come on, gravitational lensing? As soon as I mention the fact that that's not possible in free space because light doesn't travel in free space, he says, well, if you're going to go down that route, you totally just dispel everything that we've been working on for God knows how long. Sorry, I don't mean to hurt your fucking feelings, but that's the fucking reality of it, people. Yes, I'm studying applied physics, but I'm studying applied physics to develop the foundational understanding and comprehension of how they actually came about developing these papers to say what they're saying without fucking being forced to prove it. I'm moving towards a goal to prove this shit is either bullshit or I've got a new theory. And he doesn't even want to consider the fact that superfluid helium at 0 degrees Kelvin could be the fucking answer if it was combined with carbon nanotube Vanta Black in liquid form and excited to and develop some sort of electrodynamic or thermal equilibrium type of environment. And that's what space could be. 2 of the top laboratories in the United States still don't fucking know. I don't know, people. I'm going to need help on this one with somebody who's interested in this. Like I said, people, it's not what you know, it's what you can prove. And here you have it for yourself. Berkeley Laboratory. They don't want to agree with the Europeans. You saw what the Europeans had to say. They think it may be some sort of fluid. U.S. don't want to do that because it takes money out of their fucking pocket. They'll lose the capability to keep scamming U.S. taxpayers and to continuing to fund this bullshit science. It looks like Europe is more on the track of really saying, hey, let's start looking at what we've been denying could be the possibility. Space is fucking liquid, some sort of fluid. It's not, there's no particles. There's no particles. Decide for yourself, people. I'm going to put all these links to all these websites in the description section, and you guys can do your research and start looking into this, people. Like I said, it's not what you know, it's what you can prove. Peace out, people.